Thank you for coming to our talk, Monopoly Go, Crafting Enjoyment for Players. My name is Chad R. I'm the Associate Technical Director on Monopoly Go. And I'm joined with Jamie, who is a Technical Lead on Monopoly Go. What Jamie and myself want to cover in this presentation is to break down a couple of the most interesting systems that we use in Monopoly Go. So we're going to talk briefly about the game and our engineering principles. These principles govern really how we think about developing code. Then we're going to go right into a feature and describe a surface level implementation of how it's constructed on two big systems that we use in Monopoly Go. One is MVVM, and another is called client actions. And then at the end, we'll have plenty of time for questions or anything. So Monopoly Go. If you're not familiar with Monopoly Go, it is a casual social game based on the extremely popular board game Monopoly. We launched in April 2023 with one of the biggest mobile game launches ever. Currently, we're around 10 million daily active users. If you're unfamiliar with the gameplay loop too, what happens is there's a giant go button in the screen. You click it, dice get thrown on the board, your token moves around, and you acquire money. You use this money to build landmarks on your board. Then once you build all the landmarks, you move on to the next board. This is all done in a very asynchronous gameplay loop where we basically use very simple network connections as well. We layer on mini games, live ops, lots of other things, and a lot of social features because of Monopoly and the nature of how Monopoly is so social. What this allows us to do is you can play with your friends or against your friends in true Monopoly fashion. These are some of our main engineering principles. Talking through each one, it's immediacy, simplicity, and resilience. I'm going to talk through each one a little bit. Immediacy. Games, especially mobile games, but all games, have to react instantly. They have to be responsive. You have to do something and see something. Loading spinners, hangs, delays in input, all that stuff feels really bad for players. And games usually get around this by prefetching data, caching data, who knows, other techniques like that, which we do as well. Another thing that was really important with us for immediacy is that we can deliver the intended player experience regardless of connectivity. So if you're offline, if you're going in the subway, if you have a hitch, things still happen smoothly and flow smooth. This is something that is going to cause tension in game development. Game development does not have that type of principles. So we want this difficult conversation to happen on the game teams and between engineering, design, whoever, so that our players have a great experience. Simplicity. Keep it simple. Over-engineering is something we're all super, super guilty of. Often, your team, your colleagues, you have design patterns that you can leverage, that you can fall back on, and this is what you should try to do as much as possible. If you can find design patterns that work commonly on your team, you can always fall back to these and then have a reliable system so you know what works, and then your players will generally have a more stable experience. And then resiliency. This is my favorite GIF, I had to include it. Lizzie from our game. Everything fails and everything breaks. Accidents happen, mistakes happen. This is something that is life, right? Works on my machine. I don't know what happened here. It blows up on production. It's going to be out of your control, but what is in your control is what you do, or more importantly, what your code does. What does your code do to basically deal with this? Isolation of systems, separation of concerns. These are all things that generally get talked about that are implored here to make sure that things and your systems are resilient. And when hiccups happen in your game, your players have no idea that the hiccup actually happened. So now that you know kind of our principles, how we kind of approach some of our systems, I want to talk through how a feature team would make a feature in Monopoly Go. So for this presentation, we're going to go through a existing feature from Monopoly Go. It's a feature called Bank Heist. In it, it's just a kind of a classic match 3 game. Nothing super crazy, I feel. On the player's journey, when you're rolling around that board and your token's moving around the board, you'll land on a specific spot on the board. It's a railroad, specifically, and you'll get transported to this minigame called Bank Heist. In it, you get matched with a user, in this case, Donnie, and you click on one of these 12 vault doors. You click on it, the vault door pops open, and you get a little icon behind the door. Once you match 3 of the icons, you then get rewarded currency based on this tier of the heist. How do we go about setting this up on the client? We've chosen to use this architectural pattern called MVVM. This stands for model, view model, or model, view, view model. This pattern specifically facilitates the separation of concerns I was alluding to earlier. So here we actually have, you can see we have a presentation logic, is what it's traditionally called, between the view and the view model. MVVM also takes advantage of data binding quite heavily. So when one thing updates, everything on the chain updates. So the view and the view model are bound between data, and then the model is actually, when the model changes, it updates the view model. The model and what happens there is generally referred to as the business logic. With games, sometimes we call it gameplay logic. So this is that separation of concerns. If you modify the gameplay logic, the presentation logic stays the same, and vice versa. Now, stepping through each one of these kind of components, we're going to first start with the view. The view is, of course, we're here for Unity, right? So this is Unity. The view is always going to be Unity. This is kind of like a little skewed picture from the scene because I thought it was a little cool. And this is going to be where artists, technical artists, hopefully not your engineers, because your engineers should be in code, and your other teammates should be setting up prefabs, hopefully. And during normal development, you won't have final assets. You'll be working with placeholders, gray boxes, what stuff. But when your artists and everybody are working in your scenes and your prefabs, the engineers can be working on setting up more of the model. So when I say model, sometimes people think it's like one model. That's not necessarily true. Once again, separation of concerns. We want to basically separate out as much as possible these chunks of data into smaller bite-sized chunks. Smaller chunks generally tend to lead to easier to scale systems. Not always, but most of the time. These models are going to be the source of truth too. Like this is where the reward tier, the information for all of these things kind of live. You can also generally, it might help to think about models as static, that mostly contain primitive fields, like just right here. Here you can kind of see there's a pick game info model, which is more around the UI and the presentation. And then there's going to be 12 pick game item models that represents each of the picks that you can do. The model will then get bound to your view model. So here we have a view model where everything gets exposed for the view. This is usually kind of a boring file where it should almost match your model. Here you can kind of see all of those variables from the last one are here again. And everything will then get linked to the VM. So here, if you go through the code, you kind of register out the model. So when that data binding and that change gets updated, the on-model change gets fired, and all of your variables get updated. You can also see we have this thing called observable. Observables are what facilitates that data binding I've been referring to. And observables will be linked to what we call an observer. But we've talked about view model, view, and models, which is the traditional MVVM approach. So where would this kind of weird observer live? And this is where we've added more bits into what we consider MVVM. And the first one is a binder. So binders are responsible for being the bridge between the view model and the view being Unity, right? So here we have, this is a text binder, and we have many, many binders. Essentially, we have a binder for every bit, every component of Unity that we use. So we'll have a text binder, an image binder, canvas group alpha binder, animator binder. You get it. So what happens here, like on the Unity view side, you have this VM. The VM would be drag dropped into the text binder, the observer, and then you would select what observable you want to observe. Then when that changes, looking at the code, there's an add listener. When bind text gets called, bind text gets called, the text gets updated, your view is now updated to wherever the text is. This lets basically those concerns kind of be isolated a little bit, and it lets you kind of keep bind text being a clean method. But the true power of binders is when we add in this other layer. So this other layer is the concept of properties. So properties allow us to do this other cool thing. They let us be able to add logical checks to the binders. So this kind of property logic check we usually refer to as state. Maybe it wasn't the best name, but it is what it is. And with it, you can tell right here, we have this binder. Now what's happening in the binder is if the value is 0, we turn the color font white. If it's higher than 1,000, we turn it blue. The code's not pictured all here either, because we have a states binder there that does a lot of manipulation. But what happens in the background is the value being observed changes. Then we go through basically a states binder. The states binder will then call and do the state check to see what's going on, which then calls on properties, which then will change the color of the text, and then proceed and call bind text. So what this does is allows our artists and whoever's in the view in Unity to use whatever all of our binders might be to manipulate the VM values to then manipulate Unity stuff. This allows us to basically have a lot of manipulation and have things be able to live in the view. And you don't need to put color in your model. You don't need to have this thing here. This is just something that's isolated to the view, because that's where that view concern should live. And lastly, in this system, that was a boring slide, is the service. A service is what we use to create the model. And this is you can think of them as static. You can probably think of them as singletons even too. I'm not trying to trigger people with singletons, but yeah. So, and on Monopoly Go, we actually usually use dependency injection. So often what we'll do is we'll have an interface. So we'd have an pick game service. And what that will allow us to do is switch out, have a pick game service v2, v3, or do a mock pick game service, which will allow us to facilitate integration testing, unit testing, whatever. But the most important part really is that we have this picked method, and this picked method is where all model manipulation comes in. So since this is where all models get manipulated, this makes it very easy to solve a problem that we've always run into in Unity, which is essentially, it's really hard, the code, to debug things that are code versus Unity. So this allows us, all of our developers, they know if we're modifying a model that it's going to be in the matching service of that name. This really, really facilitates that kind of common ability, so everyone can debug things, everyone knows where things are, and there's no oh, it's in a controller, oh, it's in a manager, oh, it's in this. It's here. It should also be noted that there's this thing called item at index.raiseChange. Data binding is really heavy. A big reason why people don't use data binding is it's not performant, right? You can't control updates. One thing changes, everything changes. So here we've kind of isolated it, so raiseChange is what calls that data binding. If that doesn't get called, none of the data gets updated. So what we can do is we can stack changes and then call it all whenever we want, or whatever the developer wants. So here's the full journey now. So I've talked through binders, services, models, view, observables, observers. It's a lot of technical jargon. There's probably some other stuff. But what ends up happening here is if you want to tap a door, the user clicks a door. An input binder would grab that input and then communicate to the service that the door was picked through that pick method that I was just referring to. raiseChange then gets called. When raise change gets called, all the observables then get updated. When the observables get updated, then the observers that are observing them get updated, which then updates the view. So on and so on. So when you click each of the door, each of those go through that full journey. This architectural pattern is used practically in every place in Monopoly Go. Now I want to introduce Jamie, who will talk about what's next.
Thank you, Chad. So Chad showed us how we approach feature development from a client perspective. He showed us how we utilize MVVM and also services to enable our client-side development. So what comes next, right? We need to process the player's input. We need to determine what rewards they're going to receive. We need to send those results to the server, and we need to update a user state somewhere. So how do we achieve this? So traditionally, there's two kind of main approaches to this. So there's a client authoritative approach and a server authoritative approach. So if I walk you through a really simple example of a client approach, here we get a user input, it gets passed into the client. The client will run some form of simulation, determine the reward the user should get, pass that reward out to the user, and then also send that to the server where it can update the user state. So in this scenario, the server has to trust the values it's receiving from the client and trust that they're true. And the benefits here, the pros are it's immediate. So you get that immediacy we spoke about earlier. It's very responsive. It feels great for the player. But the cons are it has some security and vulnerability issues. All your processing logic lives on the client, and that's easy to exploit. So the alternative is a server-driven approach. Here, similarly, we get a user input, and that gets passed to the server. So now, this time, the server will run the simulation, determine the rewards the player gets, return that to the client, and also update the user state. So here, the pros are you have more security, you have more control over what happens. The main processing logic doesn't live on the client. But the challenges are it's slow. You don't get that immediate feedback. Maybe you have to use spinners, like mentioned earlier, and we want to try and avoid those things as much as possible. So, what can we do if we want the best of both worlds? So this is where client actions and our kind of shared simulation model comes into play. So in our approach on Monopoly, we have a common layer that's shared between the client and the server. And this is where the main kind of simulation logic lives. So you can see in this flow, we would take the user input from the client, and on the client, we would execute that shared logic. We would determine the reward that the player gets, we would show it in real time, and we'd save it in their local state. Then asynchronously, at some point, that same simulation will get run on the server, and it does a validation and checks, if everything runs, if everything came out correctly, if the values were valid, and if so, it'll tell the client this was okay, and if not, we can basically show an error and roll the user back to a previously valid state. So on Monopoly Go, typically we do these in batches at some sort of timed interval. So we'll store up a couple of them and process them at the same time. But we can also drive this through other events, returning to the app, reconnecting to the network, things like that. So the pros here are you get the immediate feedback on the player perspective. They press a button, they see a reward, it all works instantly. We get most of the security that we would get from a server-driven approach. And we get some added resiliency. So this means that we don't need a permanent network connection. So we can lose connection for some period of time, we cache the client actions, and then at a later date, we can rectify everything. So what actually is a client action? So what I have here is a super stripped down kind of bare bones example. So in the base client action class, you just have an ID, timestamp. And then we extend that out a little bit into what we call a validatable client action. And here we provide two important things. One is the validation map, and the other is the config list. So the validation map is essentially where we can define whatever criteria we want to validate against. So a common example might be the user state. So we would say on the server level, when you validate the client action, check that the user state matches from the two results. This can be extended, you can put whatever you want in there, but that's just a simple example. And then the config list is how the client communicates to the server to tell it what versions of the configs it was using when it ran its simulation. This is important so that the server can match the conditions on the client, and we always get the same output. So back to the feature from earlier. Now that we know what a client action is, let's see how we would use it. So in the example Chad mentioned earlier, we have a VM. So the flow here could be something like the player has pressed the collection button. So the VM now wants to notify the service and tells it we need a client action to process what's happened. So it calls into the service, and we create a new client action object. So this will be extended on the base one that we mentioned earlier. So here what we can do is we add additional data. What you add in here is essentially extra stuff that you would need in the common layer to generate the results you care about. So in this example, maybe you provide the information of the doors that the player picked, maybe you provide the role multiplier the user was using, and things like that. So you'd construct your client action here and then fire it off to the service. So then you get to the common layer. This is where the common executor lives, and this is where most of the main processing logic would be. So I've stripped it out here to simplify, but in the case of this feature, this is where you would take the data from the client action, so the picks that the player made, you'd run it through the simulation, you would work out what reward they should get, and you would build a result object. So you can see the result object here, it's pretty primitive. We have the money they won and the size of their prize. And then you can use that result to update the user state. So in this case, we have the inventory, and we want to give the player the money they won. And then this result will later be used by the server layer to validate the results when it runs its own simulation. So then we get onto the server, and this is kind of the final piece of the puzzle. This is where we do all the validation. So in the case of the pick game that we mentioned earlier, this validation might be very straightforward. We just want to check that the reward values match. Maybe there's something else you care about. So we run through that validation here. We do a simple check, but you can extend this to be as thorough or complex as you want. Additionally, we use this server layer for pre and post execution steps. So maybe there's a layer of validation you want to do before the client action is run, or maybe you want to send some analytics events. That's where we'd handle this. And then the process is it checks the result, and if the result is invalid, we can throw an error and roll the user back to their last valid state. And then in the thankfully more common scenario, everything is fine. The player continues, they're kind of none the wiser, and we update the remote user state, and everything continues as normal. So once we're done with all that, we end up with this. So we have a kind of client-driven experience that's driven by player input. They get instant feedback and rewards. It gives us the immediacy we're after, security and resiliency, and then most importantly, allows us to give a seamless and enjoyable experience for our players. So yeah, that's all from us. Thank you very much for taking the time to come today and listen to us.